Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand intellectual theatre of the 17th century, few dramas have proven as enduring as the contest to define the fundamental nature of light. This contest, a protracted dialectic between particle and wave, found one of its most eloquent and foundational expressions in Christiaan Huygens' Traité de la Lumière. While formerly published in 690, the treatise was composed in 678, representing the culmination of ideas Huygens had been developing since at least 659, a period in which his investigations into pendulums and wave mechanics were already reshaping physics. To approach the traité is to engage with a monument of hypothetical deductive reasoning, a work of profound geometric intuition that constructed a comprehensive wave theory from a single, powerful principle, though its brilliance was eclipsed for a century by the corpuscular philosophy of its formidable contemporary, Isaac Newton. Huygens' work contained the essential architectural elements that, upon their rediscovery, would become indispensable to the final edifice of classical optics and stand as a testament to the predictive power of mathematical physics. The intellectual landscape into which Huygens projected his theory was dominated by the mechanical philosophy, a worldview that sought to explain all natural phenomena through matter and motion. The primary theory of light within this framework was that of René Descartes, articulated in his Dioptrique of 1637. For Descartes, the universe was a plenum, a space entirely filled with subtle matter, and light was an instantaneous pressure transmitted through this medium, much like the pressure exerted along the blind man's cane. Huygens, a devoted mechanist himself, inherited this rejection of action at a distance and the necessity of a medium for light's propagation. His conception, however, diverged from the Cartesian model in a critical way. He conceived of light as a motion transmitted successively through the medium, a process that required a finite amount of time. This conviction was bolstered immeasurably by the 676 findings of the Danish astronomer Ole Rømer, whose observations of the eclipses of Jupiter's moons provided the first quantitative evidence for the finite speed of light. Huygens seized upon this empirical validation, even calculating a value for light's speed that appears in the Traité, grounding his abstract theory in the bedrock of astronomical observation. His intellectual inheritance also included the work of Pierre de Fermat, whose principle of least time offered a teleological, almost antagonistic, framework for explaining refraction. Moreover, Huygens was indebted to the Jesuit scientist Ignace Garsten Pardis, who had proposed a preliminary wave theory and whose correspondence with Huygens likely spurred the refinement of his own ideas. Huygens' task was to synthesize these elements, a finite propagation speed and a mechanical medium, into a coherent, geometrically rigorous theory that could account for the known properties of light better than its predecessor. The architecture of this new theory rested upon two foundational pillars: a specific conception of the ethereal medium and a generative principle of wave propagation. Huygens' ether was a departure from the Cartesian plenum of contiguous particles. He imagined it as a substance composed of innumerable, infinitesimally small, perfectly elastic particles packed closely together. A disturbance, or luminous excitation, at one point would cause a particle to move, which would then collide with its neighbours, transmitting the motion outward in a shockwave, or as Huygens termed it, an onde. This conception of a wave was fundamentally a pulse, a single succession of motion, a longitudinal compression travelling through the medium. It lacked the modern understanding of periodicity and wavelength, a conceptual limitation that would later prove significant. The true genius of the work, however, lay in the mechanism he proposed for the propagation of these pulses, a rule now universally known as Huygens' principle. He posited that every point on an advancing wavefront acts as the source of a new, secondary spherical wavelet. The subsequent position of the main wavefront, after a small interval of time, is the surface that forms the common envelope tangent to all these secondary wavelets. This simple, elegant geometric construction became the engine of his entire theory, a tool of extraordinary explanatory power capable of deriving the entirety of geometrical optics through a single postulate. Its first successful application was in resolving one of the most persistent challenges for any wave theory, the rectilinear propagation of light. Opponents argued that waves should spread out in all directions, bending around corners as water waves do. Huygens' principle provided a beautiful answer. While each point on a wavefront indeed generates a spherical wavelet spreading in all directions, the collective envelope of these wavelets, their constructive superposition, forms a new, sharp wavefront that advances only in the forward direction. The lateral components, in a homogeneous medium, effectively cancel one another, leading to the appearance of a straight ray of light. Armed with this powerful principle, Huygens proceeded to demonstrate its capacity to derive the established laws of optics with a rigour that was purely mathematical. His treatment of reflection is a model of geometric clarity. By considering a wavefront incident upon a plane surface, he showed how each point on the front, upon reaching the surface, becomes the source of a secondary wavelet propagating back into the original medium. Constructing the envelope of these reflected wavelets, he demonstrated with Euclidean precision that the new wavefront travels at an angle to the surface equal to the angle of incidence. The law of reflection emerged as an inescapable geometric consequence of his principle. Even more impressive was his derivation of the law of refraction, a phenomenon that had been codified empirically by Willibord Snell a half-century earlier. Huygens imagined a wavefront passing from a rarer medium, like air, into a denser one, like glass. The crucial insight was his assumption that the speed of the light pulse is slower in the denser medium. As the incident wavefront reaches the boundary, each point generates a secondary wavelet within the second medium, but these wavelets expand at a reduced velocity. Consequently, the radius of a wavelet generated by a point that reached the boundary later is smaller than that of a wavelet generated earlier. The resulting envelope of these smaller, slower wavelets forms a new wavefront that is bent toward the normal. Through this geometric construction, Huygens derived the mathematical relationship known as Snell's law that the sine of the angle of incidence divided by the sine of the angle of refraction is a constant equal to the ratio of the speeds of light in the two media. This result was a profound triumph. It explained a fundamental law of optics from first principles and, more importantly, it made a clear, testable prediction that starkly contrasted with corpuscular models. Newton's theory required that light particles accelerate upon entering a dense medium to explain the bending of their path. Huygens' theory demanded they decelerate. The experimental verdict would have to wait over a century for the work of Léon Foucault, but when it came, it would decisively favour Huygens. The crowning achievement of the Treatise, the section that showcases Huygens' genius at its most audacious and original, is his analysis of the strange double refraction exhibited by Iceland spar, or calcite crystal. This mineral possessed the bizarre property of splitting a single incident ray of light into two distinct rays, a phenomenon that had defied all previous explanation, while one ray, which he called the ordinary ray, obeyed Snell's law as expected. The other, the extraordinary ray, behaved anomalously, its angle of refraction changing with the orientation of the crystal. Confronted with this puzzle, Huygens made an intellectual leap of breathtaking brilliance. He proposed that within the anisotropic medium of the crystal, his principle required a modification. The disturbance of the incident light must generate two separate wavefronts. The ordinary ray, he posited, propagated via the familiar spherical secondary wavelets. For the extraordinary ray, however, he conjectured that the secondary wavelets were spherical, specifically ellipsoids of refraction. This was an inspired guess, a modification of his core principle tailored to fit the peculiar symmetry of the crystal. By meticulously constructing the tangent envelopes to these two sets of wavelets, one spherical and one spheroidal, he was able to account with stunning precision for the positions and paths of both the ordinary and extraordinary rays for any angle of incidence and any orientation of the crystal's optic axis. It was a tour de force of three-dimensional geometric reasoning and physical intuition, and yet, within this triumph lay the seed of his theory's temporary undoing. Huygens observed that these two emergent rays had different properties. If one of the rays was passed through a second calcite crystal, its behaviour depended on the second crystal's orientation. He described this property, what we now call polarization, as a contrary disposition between the two rays, but his model, based on longitudinal compression waves which are symmetrical about their direction of travel, could offer no mechanical explanation for this directional property. A wave that is a simple forward push has no sides, and this failure to account for what Newton would later call the sides of light became a critical vulnerability. The Traité de la Lumière met with a muted reception. Its publication was delayed by 12 years, and when it finally appeared in 1690, the scientific world was increasingly falling under the gravitational influence of Isaac Newton. Newton's own masterpiece, The Optics, published in 1704, presented a powerful, though cautiously framed, corpuscular theory that appeared to explain a wider range of phenomena. Newton levelled devastating critiques against the wave theory. He argued forcefully that waves would bend into the shadow, questioning the rigour of Huygens' explanation for rectilinear propagation. He demonstrated that white light could be decomposed into a spectrum of colours, a phenomenon for which Huygens' single pulse wave had no explanation, as it lacked the concept of wavelength. Most damningly, Newton wielded the phenomenon of polarization as a decisive weapon. How could a longitudinal wave possess the directional properties so clearly revealed by Iceland spar? Newton proposed that particles of light themselves had sides, a property that allowed them to be selectively transmitted or reflected by the crystal. These critiques, combined with Newton's immense authority, relegated the wave theory to the periphery of scientific thought for more than a century. Huygens' geometrically dense and mechanistically incomplete treatise seemed an elegant but flawed relic compared to the seemingly more comprehensive corpuscular model. For over 100 years, Huygens' brilliant insights lay largely dormant, a magnificent but unvisited cathedral of thought. Its resurrection began in the early 19th century with the work of Thomas Young, who introduced the crucial principle of interference. Young demonstrated that light plus light could, under certain circumstances, produce darkness, a phenomenon that was utterly incomprehensible for particles but a natural consequence of wave superposition. It was the French engineer Augustin-Jean Fresnel, however, who became Huygens' true successor. Fresnel brilliantly synthesized Huygens' principle of wave generation with Young's principle of interference. In doing so, he refined the principle into what is now known as the Huygens-Fresnel principle, a tool capable of explaining not only reflection and refraction but also the subtle and complex phenomena of diffraction, the very bending of light into the shadow that Newton had used as a critique. Fresnel's most revolutionary step was to propose that light waves were transverse, vibrating perpendicular to their direction of propagation. This single stroke solved the great mystery of polarization. A transverse wave possesses the inherent directionality, besides, that Huygens' longitudinal model lacked. The vindication was complete. The final physical grounding for this resurrected wave theory came with James Clerk Maxwell, who demonstrated that light is a transverse electromagnetic wave, its vibrations being those of electric and magnetic fields propagating through space. The mechanical ether, so essential to Huygens' mechanical philosophy, was ultimately rendered obsolete, replaced by the more abstract and powerful concept of the field. In the final analysis, Christiaan Huygens' Traité de la Lumière stands as a work of profound and prescient genius. It was a product of its time, rooted in a mechanical worldview and limited by the conceptual tools available. It could explain colour, and its longitudinal model prevented it from explaining polarization. Yet, its core contribution, the generative principle of secondary wavelets, was a conceptual tool of such power and elegance that it transcended the limitations of its own framework. Huygens provided the essential blueprint for understanding wave propagation, a geometric method so robust that it survived a century of neglect to become, in the hands of Fresnel, the cornerstone of classical wave optics. The treatise is more than a historical curiosity, it is a seminal text in the history of science, a demonstration of how a powerful physical intuition, when disciplined by the rigour of geometry, can uncover deep truths about the natural world, truths that may wait generations for their full appreciation and ultimate vindication.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.